best transformer connection is highly dependent upon the specific application and the requirements of that application. However, some commonly used and highly regarded transformer connections include, firstly, the delta-delta connection. The advantages of the delta-delta connection are its high short-circuit current withstand capability, and it provides a phase shift of 30 degrees between the primary and secondary windings. This can be beneficial for certain applications, such as motor starting. It can also be used for both step-up and step-down transformers. The disadvantages of the delta-delta connection are that it's not suitable for applications requiring a neutral connection, and it may exhibit higher losses compared to other configurations. Secondly, the delta-star connection. The advantages of the delta-star connection are that it provides a neutral connection, which is essential for three-phase power systems with grounded neutrals. It also reduces the line-to-line voltage by a factor of the square root of 3, or approximately 57.7%. It also offers protection against fault currents by isolating the neutral point. The disadvantages of the delta-star connection are a lower short-circuit current withstand capability compared to the delta-delta connection, and it can introduce harmonics and voltage imbalances under unbalanced load conditions. Thirdly, the star-star connection. The advantages of the star-star connection are that it provides a neutral connection similar to the delta-star connection. It offers a higher short-circuit current withstand capability than the delta-star connection and is suitable for applications requiring a neutral connection at both primary and secondary sides. The disadvantages of the star-star connection are that it may exhibit higher losses compared to the delta-delta connection, and it can introduce harmonics and voltage imbalances under unbalanced load conditions. Fourthly, the star-delta connection. The advantages of the star-delta connection are that it provides a neutral connection at the primary side only, and it acts as a phase converter, changing a three-phase delta system to a three-phase star system. It can be used for step-up or step-down transformers. The disadvantages of the star-delta connection are a lower short-circuit current withstand capability compared to the delta-delta connection, and it may introduce harmonics and voltage imbalances under unbalanced load conditions. Fifthly, the open delta connection. The advantages of the open delta connection are that it provides a three-phase power supply with reduced transformer capacity, requiring only 2 transformers instead of 3. It can be used as an emergency backup or temporary power source. The disadvantages of the open delta connection are a low power capacity and reduced efficiency compared to other connections. It may introduce voltage imbalances and harmonics, and it is not suitable for critical applications. The choice of the transformer connection depends on factors such as the voltage levels, the power rating, the load type, fault conditions, neutral grounding requirements, and system configuration. Engineers carefully analyze these factors to determine the most appropriate connection for each specific application. The delta-delta connection is often favored where a high short-circuit withstand capability is needed and a neutral is not required, for example, in some industrial applications. The phase shift provided can also be strategically utilized in specific power system designs. The delta-star connection is commonly used in distribution systems to provide a grounded neutral for safety and to supply single-phase loads from a three-phase source. The voltage reduction is advantageous for stepping down voltage levels. The star-star connection finds its application in situations where a neutral is needed on both sides of the transformer, such as in certain types of power distribution networks. Its higher short-circuit withstand is a benefit in these scenarios. The star-delta connection is useful as a phase converter and is also employed in applications where neutral is needed only on the primary side. This connection is less common than the others. The open delta connection is a practical solution for temporary or emergency power needs, or when the full capacity of a 3-transformer bank is not initially required. However, it is important to be aware of its limitations in terms of capacity and potential imbalances. Considering these connection types, the selection process also involves evaluating the impact of harmonics. Harmonics are distortions in the voltage and current waveforms that can cause various problems in electrical systems, including equipment, overheating, and reduced efficiency. Certain transformer connections, like delta star and star star, can be more susceptible to harmonic-related issues under unbalanced load conditions. Mitigation techniques, such as using harmonic filters or reactors, may be necessary to address these problems. Furthermore, the grounding requirements of the system play a significant role in determining the appropriate transformer connection. Grounding refers to the connection of the neutral point of the transformer to the earth, which provides a low impedance path for fault currents to flow, helping to protect equipment and personnel. Different grounding methods, such as solid grounding, resistance grounding, and reactance grounding, have different characteristics and are suitable for different applications. The choice of transformer connection should be compatible with the grounding method used in the system. In addition to the technical factors mentioned above, the economic considerations can also influence the choice of transformer connection. The cost of the transformers themselves, as well as the associated installation and maintenance costs, can vary depending on the connection type. Engineers must carefully weigh the technical benefits of each connection against its cost to determine the most cost-effective solution. The power rating of the transformer is another critical factor to consider. Higher power ratings may necessitate certain connection types that can better handle the increased current and voltage levels. For example, delta-delta connections are often preferred for high-power applications due to their high short-circuit withstand capability. Load type also plays a role. Linear loads, such as incandescent lighting and resistive heating, draw current that is proportional to the voltage. Nonlinear loads, such as electronic devices and variable frequency drives, draw current that is not proportional to the voltage, resulting in harmonic distortion. Transformer connections that are less susceptible to harmonics may be preferred for applications with a high proportion of nonlinear load. Moreover, fault conditions and the need for system protection are paramount. The transformer connection should be chosen to minimize the impact of faults on the system. Connections that provide a neutral point, such as delta star and star star, can facilitate the detection and clearing of ground faults. The system configuration, including the number of phases and the voltage levels, also influences the selection of the transformer connection. Three-phase systems are the most common for power distribution, but single-phase systems are also used in some applications. The transformer connection should be compatible with the system configuration. The location of the transformer is also a factor. Transformers located in areas with high lightning activity may require special protection measures, such as surge arresters, which can influence the choice of transformer connection. Lastly, the specific standards and regulations that apply to the installation can also affect the choice of transformer connection. These standards and regulations are designed to ensure the safety and reliability of electrical systems. The NEC, or National Electrical Code, provides guidelines for electrical installations in the United States, and it includes requirements for transformer connections. Specific NEC tables such as 310.15 outline ampacities of conductors, which are crucial for selecting the appropriate conductor sizes based on the current carrying capacity required by the transformer connection. Furthermore, understanding transformer impedance is crucial. Transformer impedance, expressed as a percentage, limits the fault current and affects voltage regulation. Higher impedance reduces fault current but increases voltage drop under load. The choice of impedance is a trade-off that depends on system requirements and coordination with protective devices. Also, tap changes are often incorporated into transformers to adjust the voltage ratio and maintain a stable secondary voltage under varying load conditions. Tap changes can be either manual or automatic and are typically located on a high voltage winding. The selection of the tap changer range depends on the expected voltage variations in the system. Paralleling transformers is a common practice to increase capacity or improve reliability. When paralleling transformers, it is essential to ensure that they have the same voltage ratio, impedance, and phase angle. Otherwise, circulating currents can flow between the transformers, leading to overheating and reduced efficiency. Finally, regular maintenance is essential for ensuring the reliable operation of transformers. Maintenance tasks include inspecting the oil level, checking for leaks, tightening connections, and testing the insulation. Proper maintenance can extend the life of the transformer and prevent costly failures. To summarize, selecting the best transformer connection involves a comprehensive analysis of the application's specific requirements, considering factors such as voltage levels, power rating, load type, fault conditions, neutral grounding requirements, system configuration, economic considerations, standards, and regulations. Engineers must carefully weigh the advantages and disadvantages of each connection type to determine the most appropriate solution for each situation.